Titanium is the ninth most abundant element in the Earth's crust. However, titanium is not even remotely close to being the ninth most common element in industrial commercial use. In fact, despite being so abundant, we didn't even know titanium existed until the late 18th century, and we couldn't figure out how to actually practically use it until the 1960s. It's a remarkable metal with amazing properties that still is incredibly hard to use. Learn more about titanium, the amazing yet difficult metal, on this episode of Everything Everywhere Daily.
When you listen to Nobody Listens to Paula Poundstone, the comedy podcast, you get a belly full of laughs and a head full of real information. Our gallimaufry of expert guests answer questions on stuff adults need to know. I have mold in my dwelling. What do I do? What's gerrymandering? What happens chemically when I fall in love? How do I handle a parent-teacher conference? What are microbes? Listen to Nobody Listens to Paula Poundstone. Solve problems, get laughs.
This episode is sponsored by Noom. Noom is changing the game with weight management. You're probably aware that a lot of weight programs out there focus on what you eat. Well, Noom is using science to help you understand why you eat, and that makes a huge difference. Noom uses science and personalization so that you can manage your weight for the long term. Noom takes a psychology-based approach that helps you build better habits and behaviors that are easier to maintain. And the best part is that you decide how Noom fits into your life, not the other way around. Noom's personalized courses are easy to follow and will help you grow your confidence with tools you can put into practice on day one. They give you the knowledge and wisdom you need to make informed choices about what you eat. Based on a sample of 4,272 Noomers, 98% said Noom helped them change their habits and behaviors for good. Sign up for your trial today at Noom.com. That's Noom.com to sign up for your trial today. Noom.com. Titanium is the 22nd element on the periodic table. It's a silvery metal that looks very similar to steel in its pure elemental state. It has a very good strength-to-weight ratio, and it's highly resistant to corrosion. It's a relatively poor electrical conductor compared to other metals, and it doesn't expand or contract much when temperature changes. It is also non-toxic and is considered to be biocompatible, which, as we'll see in a bit, has many useful properties. It is the ninth most abundant element in the Earth's crust and the fourth most abundant metal. The short story about titanium is that it's a metal with really attractive properties, and it's very abundant. You would think that such an attractive metal would have been used throughout history. However, you'd be wrong. No one had a clue that titanium even existed for most of human history. The reason why titanium remained hidden had to do with its chemical proclivity to bond with pretty much anything. This is almost the opposite of how gold reacts, which is why gold is almost always found in its natural metallic state. If you remember back to my episode on aluminum, it's the opposite of gold, and it's very similar to titanium in that pure metallic aluminum almost never exists in nature. The difference between aluminum and titanium is that whereas there were very few examples of pure aluminum, there are no known examples of pure titanium. Humans in history were aware of and did use compounds that contained titanium, but at the time they had no clue what elements were or that such compounds were made up of more elementary things. The person who's credited with the discovery of titanium is British clergyman and mineralogist William Gregor. In 1791, he was studying samples of sand from Cornwall, England, when he identified two oxide metals in the sand. One was iron oxide, and the other was a white metallic oxide that he couldn't identify. He eventually concluded that this oxide must contain a new element. He published his findings and named the new substance monaconite. 4 years later, the German chemist Martin Heinrich Klaproth came across the same oxide that Gregor had discovered. He too recognized that the material must be a new element, which he named titanium, after the Titans of Greek mythology. Later, Klaproth heard of Gregor's discovery and obtained a sample of the sand that Gregor had studied from Cornwall and found that it was also titanium. Klaproth credited Gregor with the discovery of titanium, but it was his name for the element that stuck. Both Klaproth and Gregor had identified that there had to be a new element in the compounds that they studied, but neither of them was actually able to isolate the element. Neither of them ever saw pure, actual titanium. For over 100 years, chemists continued to study titanium, but no one was able to actually create a sample of pure titanium. They could get it to bind with other elements, but they couldn't isolate it. There were certain things that they were able to learn about titanium from these studies, but they weren't able to determine its most important properties without pure titanium. They were, however, getting close. By the 1880s, Swedish chemists were able to make 94% pure titanium. It wasn't until 1910 that Matthew Hunter, a scientist at General Electric and the Rensselaer Polytechnic Institute, used a variation of the Swedish process to finally produce metallic titanium. He was searching for new potential light bulb filaments. His process, known as the Hunter process, involved heating titanium tetrachloride with sodium at temperatures as high as 800 degrees Celsius or 1500 degrees Fahrenheit at very high pressures. This allowed for the creation of titanium with purity levels over 99.9%. While this was a breakthrough, and it finally allowed researchers to study titanium as metal in its pure form, it really had no practical application. The process was too difficult, and it could only produce very small amounts. The idea of using titanium for something like a golf club was still a long way away. The breakthrough in the ability to create titanium for industrial use occurred in 1930, less than 100 years ago. A scientist from Luxembourg named William Kroll was running experiments with titanium. Over a period of years, he developed a process of reacting titanium tetrachloride with magnesium in a vacuum chamber. Known as the Kroll process, it creates an end product that is called a titanium sponge. It's called a titanium sponge because it's very porous and looks like a sponge, not because it's actually absorbent. A titanium sponge is mostly pure titanium with some other impurities, mostly magnesium, that needs to be further refined. However, it's a starting material and the biggest part of making titanium. By 1938, Kroll had been able to make over 50 pounds of pure titanium metal, and used that to make simple metal objects such as wires and titanium plates. In the 1940s, the U.S. Bureau of Mines began to investigate ways of producing titanium, and determined that the Kroll process was the best means of commercial titanium production. And while it's been improved over the years, the basic Kroll process is still used today. During the Second World War, the Bureau of Mines was making 100 pounds of titanium per week using the Kroll process. 100 pounds a week is still not a lot of metal. You couldn't really build anything out of it, but it did vastly expand the ability to conduct engineering experiments with the metal. Samples were sent to laboratories, and researchers discovered many of the things that I mentioned at the start of this episode. It was as strong as stainless steel, but weighed 40% less. It was resistant to corrosion, and it performed well at high temperatures. People began envisioning airplanes, ships, and vehicles made out of titanium, and some thought it could replace both aluminum and steel in industrial production. The press called titanium the wonder metal and the miracle metal. In the early 1950s, at least 24 companies in the United States announced plans to create titanium. It was the tech boom of that era. However, there was a problem. Titanium production was never able to match expectations. Only 75 tons of titanium was produced in 1951, despite a demand for over 30,000 tons. Besides the big problem of simply making titanium, now that they had some actual metal to work with, they found another very significant problem. Titanium didn't behave like other metals. Everyone had just assumed that they could repurpose the same machines that were used for stainless steel production. Metal is metal, right? Well, it turned out that working with pure titanium was nothing like working with steel. You couldn't forge, stamp, roll, or grind titanium like you could other metals. For example, when drilling titanium, if you drilled it at speeds used on normal metals, the temperature would rise dramatically, which damaged the drill bit. So you had to drill slower, which took much more time. This made making anything extremely difficult. The first attempt at trying to make a panel for an aircraft resulted in a sheet of metal that could be ripped apart like a piece of paper. All of the dreams about the miracle metal revolutionizing the world were falling apart. The failure of pure titanium led to trying to find titanium alloys that would be easier to work with. The eventual alloy which was discovered, and is still the most popular today, is 90% titanium, 6% aluminum, and 4% vanadium. Perhaps the biggest event in the history of titanium was the development of the high-speed reconnaissance spy plane known as the Lockheed A-12. The A-12 was the predecessor to the SR-71 Blackbird, which was the subject of a previous episode. The A-12 was to be the fastest aircraft in the world, something that could outrun any enemy missile. As such, it would need to be very lightweight and have a skin that could handle the high temperatures that would be created due to friction. Titanium seemed to be the perfect metal for the job. This was the biggest titanium project ever by a wide margin. Prior to the A12, titanium was primarily used for small parts in jet engines. The A12 was to be 93% titanium by gross weight. Construction of the A12 required the development of new techniques for using titanium, and the discovery of even more problems. For example, they discovered that water with chlorine in it actually caused the welds to weaken. Titanium bolts would have their heads pop off if they were tightened with cadmium-coated wrenches. Every time one problem was solved, it seems they created another. A full 95% of the first 6,000 titanium components created for the A12 couldn't be used. Eventually, they did solve many problems of working with titanium. The creation of the A12, in a very literal sense, spawned the creation of the titanium industry. It was from the production of the A12 that a base of knowledge was created in milling and working with titanium. Another major discovery regarding titanium was made in 1952. In Sweden, an experiment with rabbits accidentally found that bone would bind with titanium metal. This process, dubbed osseointegration, had never been observed before. It had previously been assumed that the body would reject any foreign substance. Further experiments found that the body didn't reject titanium and that there were no negative consequences. Today, titanium is used for screws and plates to mend broken bones as well as in dental implants. Throughout the Cold War, titanium was classified as a strategic mineral, so its use was limited. The U.S. Department of Defense actually created a strategic stockpile of titanium sponges. These were to be used in projects which were deemed to be sponge-worthy. When the Cold War ended, titanium was reclassified, and in 2000 the titanium sponge reserve was sold off. The end of the Cold War and the reclassification of titanium away from being a strategic material changed the market for titanium. Whereas titanium was only used for high-value items like aircraft parts, titanium was now available to be used for other purposes, such as golf clubs, tennis rackets, and bicycle frames. The biggest use of titanium today, by far, is titanium dioxide. Titanium dioxide is a very white pigment. A full 95% of all titanium that is mined will end up as titanium dioxide. Titanium dioxide is used in paints, plastics, paper, cosmetics, and even in toothpaste. It is extremely white, which means that it can reflect light and heat very well. The exterior of the Saturn V rockets used in the Apollo program was painted with titanium dioxide. Titanium is a very odd element. It's very common in nature and has amazing properties, but it never fulfilled its promise as the wonder metal. It never became as widespread as a similar metal that gained popularity in the 20th century, aluminum. One big reason titanium isn't used more is that it's just really hard to work with. More important than that is the fact that titanium still remains relatively difficult to make, as we've never developed a process substantially better than the Kroll process. If someone could develop such a system, it would have the potential to usher in a true titanium revolution and finally allow this wonder metal to fulfill its promise. The executive producer of Everything Everywhere Daily is Charles Daniel. The associate producers are Thor Thompson and Peter Bennett. I just want to thank everyone, including the show's producers, who support the show over on Patreon. If you'd like to support the show, just head over to patreon.com, which is currently the only place where you can get show merchandise. Also, if you want to talk to other listeners about the show, head over to our Facebook group or Discord server, both of which have links in the show notes.